All right. Hi, everyone. My name is Giulia. I am an AstroCamp alumna. I was there in 2019. And I was a summer intern at NASA this summer. My internship actually just ended a couple of days ago, which is so sad. I have to say I was, not I am. And I'm also an undergraduate student at Rice University. And I'm here to talk a little bit about my summer research, which involved estimating the radius and mass of neutron stars using machine learning. Oh, okay, it worked. Nice. Before I start, I just wanted to thank Professor Carlos for giving me this opportunity and just start giving you guys a bit of an outline of this presentation. So first, I'm going to tell you guys who I am. Then I'm going to talk a little bit about neutron stars and why they are the coolest, most fascinating objects ever. Then I'm going to talk a little bit about NICER, which is my mission at NASA. Then I'm going to talk a little bit about my project, the next steps, and parallel work. And by parallel work, I mean, I'm going to talk a little bit about what other scientists who are not exactly in my research branch are doing and why that is so cool and how it all comes together in the big picture of things. And finally, I will tell you guys a little bit about how you can apply to work in NASA at different stages of your career. Hopefully we have some people who would like that and are excited about NASA. I was a big fan because before I was hired. So hopefully you guys have this opportunity too. So first, who am I? Well, I'm gonna start talking a little bit about who I was in high school when I went to AstroCamp. I am from Brazil, mostly spent most of my life there. I wanted to emphasize that I only have one citizenship, and that's my Brazilian citizenship. I'm not an American citizen. I am not a permanent resident, which means that you can work in NASA even if you're not American, even if you don't live in the United States, even if you're just like from any other part of the world, really. Yeah, as I said, I went to AstroCamp in 2019. This is a quick disclaimer about different education systems. High school only lasts 3 years in Brazil. So I was halfway through my second year of high school when I went to AstroCamp. I know that the educational systems are very different. So that was equivalent to like halfway through your junior year in the United States. I think it depends a lot on what country you're in. But yeah, when I went to AstroCamp, I wanted to be an engineer and I was not actually considering being a scientist, but I was participating in science Olympiads. So this is also an advertisement for that. I feel like most countries have a set of science Olympiads of diverse subjects like math, physics, astronomy. My favorite was the Astronomy Olympiad. I classified to participate in the International Olympiad in Astronomy and Astrophysics. But then COVID happened. I went to the virtual version instead, which is JECA. But participating in stuff like that made me see that I really wanted to be a scientist. And then because of my medal, I was able to get into a really good university in the United States. And then that brings me to my college career. I am a senior at Rice right now in Houston, Texas. As I said, the educational system in America is a bit different from the European system. So all majors here last 4 years. So you stay in undergraduate for 4 years, and then after that you apply for a PhD for a scientist. If you're an engineer, you can get a master's. You go do something else in general, but if you're doing astrophysics or physics, you usually go straight into a PhD. So I'm studying astrophysics and minoring in computational applied mathematics. And for the first 2 years of my college career, I was also studying computer science. I decided not to follow through with that just because the last class that I had to take in order to get my degree were really focused on industry applications and industry jobs, and that's not really what I wanted to do. But I'm still really interested in that, and that's relevant because my project is about machine learning. Yeah, and then recently I became a summer intern at Goddard Space Flight Center. So this is a map to kind of like place you guys geographically. I know not everyone is familiar with American geography, and NASA has a lot of different centers all across the country. I think the most famous one is JPL, that is tied to Caltech in Pasadena, California. But we also have Johnson Space Center in Houston, where I live. That's the center that is in charge of mission control. So there's that really famous line, Houston, we have a problem. And they're calling Houston because all the communication between NASA and the astronauts happens in Houston. So I'm just really privileged to be like 20 minutes from Johnson Space Center. I think that's really cool. They also have Kennedy Space Center in Florida. That's where they launched the rockets. Another important one is Marshall Space Flight Center in Alabama. I'm going to talk a little bit more about it later. But the coolest, most amazing one is Goddard Space Flight Center in Maryland. And that's where I've been working for. It's right next to Washington, D.C., the capital of the United States. So this is my team that I worked with this summer. There's some more people. The structure is kind of like there's the nicer team that has a lot of people working in different things. So you have like the engineers who built NICER. NICER is a telescope. I'm going to tell you a little bit more about that later. There's the people who design the mission, the people who work on time of observation requests, the people who work at like pointing the telescope to targets. And then there's a scientific branch. And within the scientific branch, there is my team. So we have Dr. Cole Miller, who is not at NASA. He's at University of Maryland. And that's a point that I think is really cool. People at NASA are always collaborating with people from other institutions all around the world. So even though Cole is not at NASA, he's super relevant and we all work with him. Like people from NASA work with him all the time. So he is my mentor's mentor. My mentor is Dr. Joanna Berto. She is a postdoc at NASA. And then right after that, you have me, the summer intern. So, okay, now I'm going to tell you guys a little bit about neutron stars. Eliana talked a little bit about them, but I am going to give you my spiel too. So neutron stars are very compact objects. They are the remnants of the core collapse supernova of a supergiant star. So if you have a really, really massive star and it collapses in supernova, it becomes a black hole. And if you have a star that's not that massive, but massive enough that it's not going to become a dwarf, it becomes a neutron star. So it's kind of like that intermediate range of mass. And they have a radius of the order of 10 kilometers and a mass that's similar to the solar mass. So they're very, very dense. Their density, their average density is comparable to that of an atomic nucleus. But because they're so compact, you can just like look at the emission from a neutron star and just assume that that's coming from the classically visible part of it. If this star was classical, you would see the emission just from the right half of the star in this picture. But because they're so compact and they generate this kind of like curvature in the space-time, you can see some light that's coming from behind. So whenever you're looking at emission from neutron stars, you have to take that into consideration. There is a ray tracing algorithm that scientists use to model that. It's like a code with like thousands of lines. I took a look at it one of these days. I think it was like 3,000 lines, and that's quite a bit. So it's quite complicated to deal with that, but it's something that you have to take into consideration. And that is tied to how compact, the effects are really tied to how compact the neutron star is. So as an example, these two stars have the same radius, but they have different masses. So they have different compactnesses. So for the star on the left, it's not that compact, it's not that massive. So you can barely see these hotspots on the surface of the star. While for the star on the right, it's more compact. So you can see more light coming from behind because the curvature is stronger. So you can clearly see both of the hotspots. For my project specifically, we work with inverse compactness, which is similar to compactness, but it's just that for some reason, for a specific reason, the calculations are just easier if you work with inverse compactness instead of compactness. But as you can see from this equation, if you have the mass and the inverse compactness of a star, you have the radius because they're intrinsically tied. So why are we trying to find the radius and mass of neutron stars? What is that going to help us with? We're basically trying to determine the equation of state of neutron stars. Eliana talked a little bit about it, but what happens is that we don't actually know how the matter in the interior of neutron stars behaves. I told you guys that the average density of a neutron star is comparable to an atomic nucleus, but the outer layers of the neutron star are not as dense as the inner layers. So while we know the composition for the outer layers, we don't actually know what's happening in the core of the neutron star. And the reason why that's so interesting is because if we can understand how really dense matter behaves, we can bring that to Earth and better understand dense matter on Earth. We can really replicate the same conditions that we have in the core of neutron stars, but we can deal with matter that is not as dense, but still very dense and better understand how that works. I also just wanted to highlight a misconception. Some people think that neutron stars are just made of neutrons because of their names. And the name just means that you can have like the pressure in the interior of neutron stars is so big that sometimes you have electrons and protons combining and generating free neutrons, but they're not just made of neutrons. There's much more inside a neutron star. So the whole point is if we can find the mass and the radius of the neutron star, we can place it here on this diagram and find constraints for the proposed theoretical models for equation of states. But we have to be really accurate when we're doing that. If you look here and you have like a star with a mass of 1.5 solar masses and a radius of 10 kilometers, you're favoring the blue model. But if the same size, if a star with the same mass has a radius of 13 kilometers, now you're favoring the other two models. So we have to be really accurate. And how are we going to do that? Like you can't really image a neutron star that is hundreds of parsecs away and resolve it because they're too tiny. You cannot just measure the radius from that. So what we do is we look at their emission, at their waveforms using NICER. So NICER is an X-ray telescope that was developed to try and understand the composition of neutron stars. The name is Neutron Star Interior Composition Explorer. I'm sorry about that. There's a composition there. That's the C. I don't understand why the last star is capitalized. It always bugs me a little bit, but it is what it is. So NICER is a really tiny telescope. I'd say it's the size of like 8 shoe boxes, kind of like concatenated. It's at the ISS. It was launched in 2017. And I think a really impressive statistics is that 61% of the Earth and Space science papers published in 2022 that use data from the ISS payloads used NICER data. Because NICER was not meant to be a huge project, but it kind of became a huge project. They're using NICER not just for neutron stars nowadays, but also for some different applications like galaxy transients and AGNs, active galactic nuclei. So I think that's really cool that we're like doing much more science than we expected to. And another fun fact about NICER is that it's always operating. So NICER is always pointing at something. A couple weeks ago, I got a chance to see kind of like their mission control room, and you can see NICER like just like moving really fast and like seeing new targets all the time. And it's really nice because you can get the data from NICER like 10 minutes after the observation. It's really a really impressive equipment in my opinion. And okay, now I'm going to talk a little bit about our work. So neutron stars have these hotspots on their surface that are at a different temperature than the rest of the star, and they have a really strong emission in X-ray. So my research group is working with modelings that have 2 or 3 hotspots on the surface of neutron stars. As you can see here, like these colored things are the hotspots in this theoretical model of a neutron star. And these hotspots can vary in radius, temperature, and location. So those are like 4 parameters total, and they affect the photon counts. Because as I said, if you have a different temperature, you're getting a different type of emission. And a different area for a hotspot means a different number of photon counts generated at that temperature. So they all impact how many photons you're getting at a specific wavelength. And just wanted to highlight another thing. I don't know if you guys are familiar with the phenomenon of pulsars, but if you have really fast rotating neutron stars whose electromagnetic emission axis and the rotational axis are not aligned, you have this lighthouse effect, and then you can see this phenomenon of pulsars. And these stars rotate really fast. I'm talking about a period of like the order of a millisecond. So you can see a really strong emission in radio that is very stable. And as you guys know, I think like radio and X-ray are on opposite sides of the energy spectrum. So doing this analysis in X-ray also means that we're looking at the hotspot emission because that's dominating over whatever emission the pulsar itself has, the neutron star itself has. So, okay, this is an example of the impact of changing the parameters and how many photons you're getting. So this is for stars that have a singular hotspot with fixed parameters. So you have stars that are changing in radius and mass, but they all have the same hotspot in the same location with the same temperature and the same radius. And as you can see here, there's a clear trend. If you have a star that's less compact and more massive, you get more photons, more counts. But it's not that trivial to just like look at it and say, oh, I know exactly what's going on here. I can like model that easily. So you have to take a little bit more you have to put in some more work to understand what's going on. And this is for one hotspot with fixed parameters. When you have 3 hotspots with changing parameters, with varying parameters, this gets messy. So what we're doing is, since we can just look at it and say, oh, I know exactly what are the properties of the hotspots and the stars, is we're creating models, waveform models for the emission of the X-ray hotspots. We're comparing that with data, and then whichever is the best model, we're looking at it and we're like, okay, these are the parameters that we're going to take as the real parameters for this neutron star. But the problem is the physical simulations involved in this process are very computationally expensive and very time consuming. So what we're trying to do is optimize the process as a whole. As I said, like the process has a lot of steps. There's like the ray tracing algorithm, there's the generation of the waveforms, there is the comparison of the waveforms, there's a more observational side that I am not that familiar with, but you have to like do background subtraction, a lot of different types of analysis. So my project is really just focused on the first part of this process, which is generating the waveforms and trying to speed that process up. So what is a waveform? I think I mentioned waveforms a lot of times here. And the definition that we're using for this project is a waveform is a lot of different light curves stacked. So each row here in this image is a light curve at a very specific energy. And the energy is ranging from 0.3 keV to 1.2 keV. And this is for one rotation of the neutron star. And I just wanted to highlight how cool that is, because as I said, like a rotation here could have a period of a millisecond, and you're getting like this amount of data that's very like very accurate for each data point that you have, for each phase point that you have. So as you can see here, you have kind of like 2 wings that have more photon counts, and that is the hotspot emission. So that's basically when you can see the hotspot. And here in the middle, when the counts are approaching 0, that just means that the hotspot is behind the star, so you can't really see it. You're not really getting that sort of emission. So, okay, to try and explain how I generated the waveforms, I'm going to walk you guys through the process that we used. So first, I have to explain what a decision tree is. A decision tree is just a data structure that performs consecutive binary evaluations that are determined based on your training data. So in this case, we use 2 inputs. We use the inverse compactness and the mass, and then we generated decision trees that evaluate that and generate a waveform. The most efficient decision trees are well balanced. They're called AVLs, and that basically just means that if you have a node and you have 2 branches coming from it, the depth of each one of these branches is going to be roughly similar to the depth of the other branch. So they're not just like skewed or crooked. And you usually have no control over their structure. So if you're using a method from a library, what happens is the computer just finds the optimal split, and you don't have to worry about building the decision tree itself. So that takes me to the random forest regressor, which is a machine learning technique that we used. The random forest regressor is basically just an ensemble of trees that are built independently of each other. So you generate 100 trees. No, in this case, we use 100 trees, but yeah. You generate trees independently from each other. So each one of them accesses different specific waveforms from training data and comes up with their own binary decisions. And then after that, each one of them comes up with a final prediction, and you average that. And that's what we're going to use as the final prediction of the model. So I don't know if you guys are familiar with time complexity of algorithms, but the time complexity here is O of n log n, because that's the efficiency, that's the complexity of generating a binary tree, which is just much more efficient than what we were using before, which is just generating the waveforms based on the sampling of the parameter space covering the entire parameter space. So our model used mass and inverse compactness as the input. I said before that we can work with like 12 parameters because you have all those hotspot parameters. But what we were trying to do here is to come up with a framework that works for 2 parameters. And then after that, expand and add some other parameters and make the simulations more efficient. And yeah, the output was the entire waveform. So I will highlight that the waveforms are 32 by 94, actually 94 by 32. So that's 3008 pixels. So this is equivalent to generating an image of 3008 pixels, which is a lot of pixels. So we needed a lot of computational power. We used 100 trees. The depth is unbounded, which means that each tree was able to perform as many operations as it wanted to. We worked with inverse compactness between 4 and 5.25, mass between 1 and 2.4 solar masses, and 2 GPUs from the NASA Center for Climate Simulation, which is a supercomputer cluster. That's a lot of computational power. And, well, how do you determine if that prediction is good enough? We looked at the Poisson log likelihood of all bins, which means that for each predicted waveform, we looked at each pixel and compared that to what was predicted, what was the test data model, theoretical model that we were trying to reach. So here, lambda is the expected counts in a specific bin, and x is what you actually observed in that specific bin. So we did that between the predicted waveform and the model with itself. There's this property of the Poisson likelihood that it is maximum when x and lambda are the same. So that would be between the model and itself. And we're basically just trying to calculate how far from the best model we are. So we took the difference between those two evaluations, which we call the delta log likelihood. And we said that a model is accurate enough if that delta is less or equal to 1. As of right now, we have like approximately a quarter of them that are accurate enough. And we're trying to come up with an algorithm that works better because a quarter is just not enough for now. As you can see here, most of them have a delta log likelihood that's not that big. So it shouldn't be too hard to bring them down by a bit. But then you have some predictions that are just really inconvenient that have a delta log likelihood of like 300. And that's not amazing. And we're trying to work on that. And this is not the end. Yeah, I asked my siblings if you guys would know about One Direction because I feel like I'm getting old. And hopefully you guys still do. I'm a big fan of One Direction. So yeah, next steps now. How are we going to solve that? How are we going to make the results more accurate? We have this one idea, which is working with more regressors. So you're basically just splitting the waveform into smaller waveforms, and you're working with multiple regressors. So what you're doing essentially is just processing smaller images and then combining the results to create a different waveform. You're adding some layers of pre-processing, but that shouldn't impact how efficient the algorithm is. Another idea is working with a neural network. This is what my mentor, Joanna, has been working with. I honestly don't know the details of the algorithm itself because it's more intricate than my regressor, and she's been working on this for months. But an advantage of a neural network is that you can train it in batches, so you can keep reprocessing it and making it more and more accurate. Now talking a little bit about parallel work. So like people who are not in Cole Miller's branch, but have been working on similar things. So there is this one specific pulsar, J0030 plus 0451, that was the first one that the NICER team ran this analysis for. And then they had two different groups do that. One led by Dr. Miller, who is my mentor, and the other one ran by Dr. Riley, who I think is based in the Netherlands. So they use different constraint parameters for the hotspots. So for example, Miller's model allows for up to 3 hotspots, while Riley's model only allows for 2 hotspots. And also the shape constraints are different. And then they publish their results kind of like at the same time. And it's really important to have this type of analysis because sometimes you assume things to get to a result that might not be the most accurate. So if you have 2 different results, that 2 different independent processes that have similar results, then you know that your analysis is good. And as I said, we're trying to be really accurate here when determining those values. Another study that is a bit different is done by Konstantinos, who is also at NASA at Goddard Space Flight Center. And he's working on lifting degeneracies. Basically, when you run the entire analysis and you come up with the parameters for the hotspots, you might get like 2 or 3 different models that both work really well for your data. So what he's doing is he's looking at a different wavelength. He's looking at gamma ray emissions, and he's modeling that based on the magnetic field of the pulsars. And then based on the fit of the gamma ray observations of the pulsar, he is kind of lifting that degeneracy by seeing what models fit the gamma ray emission best. And then finally, I hope you guys have been excited for this part. I will tell you a little bit about how to work in NASA. This is very focused on GSFC, by the way, because that's the one I have information for. That's where I worked. But I know that some of these programs exist for different centers, and I'm sure that different centers have some other programs that I'm not aware of. So first one, branch out. There's so many different branches in which you can work. So I was working in the Sciences and Exploration Directorate, and then we have like sub branches within that. We have the Computation and Informational Sciences and Technology Office, Earth Sciences, Astrophysics, Heliophysics, and Solar System Exploration, which is basically working with exoplanets. But there is also a lot of opportunities in different types of work. So there's like an entire engineering division directorate. There's the flight projects directorate, and there's so many different ways of being involved with it. The first program that I'm going to talk about is for US citizens only. I don't know if any of you guys is a US citizen, but if you are, you can apply as a high schooler or an undergraduate, or I think at any point in your career. So yeah, the Pathways program I know is not exclusive to GSFC. I know that at least like Johnson has also they also hire some Pathways students. And this is a really cool program because they usually offer return offers for posterior summers or for a real job right after you graduate. As I said, like a lot of engineers do not pursue grad school, they go straight into industry. And then this is a good opportunity if that's something you're interested in. And yeah, they operate with multiple locations. I think Kennedy also has a Pathways program. Then there's CREST, the best, the coolest, and the one that I'm a part of. So CREST accepts citizens of most countries. Basically, your country has to have good diplomatic relations with the United States. So if you're from a country that's in a war with the United States, I don't think you qualify, but most countries do qualify. And they accept scientists at multiple different stages of their career. I'm an undergrad. Joanna is also part of CREST because she's from France. She's French. She's a French citizen. And she is a postdoc. I will highlight though that for the specific program that I applied for CREST, you have to be studying in a US-based university. So I only qualified because I'm from Rice. But the fact that I was Brazilian was not an issue. So I know they have CREST for GSFC. I don't know if other centers also have that. But yeah, this is the one that like takes the most international students from what I know. And international citizens have an earlier deadline for applying, but the deadline is in the spring. So if anyone here is interested, you'd have to wait until next semester anyway. The other one is networking, which I think is a really cool one. So I have this friend who has been working with me. Her name is Junggun. She's from South Korea, and she goes to school in South Korea. She's an undergrad just like me. And she's been working. I got her, and I said, how did you get that? Because I thought you had to like be in a US-based institution to work at NASA. And she said, no, there's this one scientist who's tied to my home institution, but they actually work at NASA. And then since I'm working with them, I was invited through CREST, so like hired through CREST to join NASA. So that is an opportunity. If you guys have anyone in your institution who's tied to NASA, you could reach out to them, or you could just cold email someone at NASA, someone who's doing something you're interested in working with, and they could maybe hire you for CREST. And then finally, join missions. NASA works with agencies across the entire world on different missions. So, for example, ESA, JAXA, the Italian Space Agency. I know this is a very specific example, but that's because a couple weeks ago, I went to this workshop. It was a NICER XP joint workshop. And there were so many people who are in Italian-based institutions who have been working with NASA because XP, the Imaging X-ray Polarimetry Explorer, is a joint mission between NASA Marshall, which is in Alabama, as I said before, and the Italian Space Agency, ASI. So even though you might not be like working on site at NASA, you're still like working with them. And I think at some point you might even like be able to come to the States and work here for like a summer or for a semester. And I think that's also a really cool opportunity that you guys can look into, especially if you are based in Europe, because there are a lot of those collaborations. Yeah, thank you so much for the attention. You can reach out. Don't hesitate to reach out. I am just 20. I am not intimidating. I'm not old enough to be intimidating. So yeah, reach out if you have any questions. You can ask them here now too. But if you do reach out, don't misspell my name. I get so upset when people do. It's I before you. But yeah, that's my presentation. Thank you.